The second speaker is now Professor Adelio Mendes. And Professor Adelio Mendes is currently professor at the University of Porto. One of the objectives of Adelio Mendes is to work on the third generation of solar cells, which are cheaper, thinner, and potentially more efficient than the ones currently used. To achieve this ambitious goal, Adelio Mendes coordinates a large research team of research with research interest mainly in dye-synthesized solar cells and perovskite solar cells, photoelectrochemical cells, and solar redox flow batteries. Adelio Mendes shows an impressive scientific production recognized by prestigious advanced research grant from the European Research Council in 2012. And today his talk is entitled Electricity from Renewable Sunlight, Cheaper and Cleaner. Please.
Good morning to everyone, and thank you for the kind words of Mr. Chairman. And I'd like first to acknowledge the invitation, kind invitation for this symposium by Rodrigo Martins, Professor Rodrigo Martins. My talk is about renewables as well. I hope to bring something new after this excellent presentation by Professor Wagner. So first, a few words about the need for moving to renewables. The concentration of carbon dioxide is growing up very quickly. It just increased by 30% since 1960. So something must be done. If you allow me just 1.2 minutes, and you see the color changing. So reddish means higher temperatures, both the average and bluish at lower temperatures. So now we are over the First World War. This is from NASA. We are in the Second World War, and the planet is warming up. In the 70s, the temperature goes down a little bit for some reason. But after the 70s, it's going up and never stops. I found this movie especially illustrative of the reason why we are here. So, but good news is the emissions of carbon dioxide now, they level out. You see, the 3 last years, there is no more growth, which means something. So things are changing. First was growing up every year, now stabilizes. We hope next is going down, hopefully. So you may, now I explained the need for moving for renewables. The question is, what are the advantages? So like before, I present here the Europe, and you can see in the reddish where the electricity, levelized cost of electricity from photovoltaics is cheaper and goes up in price because the irradiance. But in the right hand side, you can see the countries where you have a positive difference between the price of the grid and photovoltaics. So where the photovoltaics are cheaper than the grid. And you can see the reddish ones, it's where you you have cheaper photovoltaics. This is 2012. Nowadays, I didn't find anything more recent, but the figures are improving all the time. So you can see here for Germany, so the blue line is for the grid, and met, the price of photovoltaics around 2011, and with storage met in 2016. That's an amazing plot. And this plot, it's from Bloomberg, December 2016, and you can see that the photovoltaics just become cheaper than wind electricity for the capex. This is for 58 countries, namely India, China, and Brazil. And for Chile, you can have electricity for almost half the price of the coal. So normally we think coal is cheapest electricity. Well, photovoltaics in Chile, it's almost half of the price. Chile has very special conditions, very dry, very high, lots of irradiance. Anyway, it's half of the price. So you can see here, I highlight the solar for farms, solar energy for farms, photovoltaics, sorry, and for domestic use. This is 2015, but the forecast for 2050 points out that the photovoltaic electricity, the levelized cost of photovoltaic electricity, it's probably the cheapest one among all other sources, including, fossil sources, so like natural gas. So I like very much this picture. I picked up this picture short ago, and you have a shop, 1 kilo of rice, and by the way, photovoltaic panel, because they are really cheap now. So just one word about photovoltaics. Photovoltaics is not only silicon. There are other technologies, but I'd like to highlight especially two less known technologies. Normally, we understand silicon technology as not being very pleasant for facades. You have facades with this technology, but they are not especially pleasant. But you have dye-sensitized solar cells. It's a recent technology, and it's entering right now in the market. There is a company, a Swiss-based company that are now producing commercially. So, and they have this nice, aesthetics. The practical efficiency is still quite low, so in the range of 4%, sometimes even less than that. But yeah, the reported maximum efficiency was 14. So in the next years, this performance may increase. This is for a niche market. This is not, for a mass market. But anyway, so H Glasses, the company in Switzerland, and you have, for the Milano exhibition, you have this nice panel with different colors that also produce. So that they have a function, and besides that, also produces electricity. More recently, we have the perovskite solar cells. While the silicon panels, they have a thickness, the crystalline ones around 200 microns, you have everything packed in 350 nanometers of absorber and some more layers, so total less than 1 micron thickness. You have everything, and you move from 3.8% in 2008, and this is last year results by Professor Michael Gratzel in Switzerland, and he obtained 21.6. And one thing that many people point out is the stability of this technology, and you can see at 85 degrees kept constant for 500 hours, and stability still improving. And recently was reported a lab-size photovoltaic cell with 22.1% of efficiency, confirmed efficiency for this pair of skies. And the expectancy for this technology is around 27% of maximum efficiency. One amazing feature of this technology is the photovoltage. You have 1.24 volts, far higher than the silicon, and this may be of interest for some applications. But I'm going to speak now about storage and how we can combine storage and harvesting. So Nature journal elected storage as the problem challenge, the present challenge in 2015, and actually it is. And here we have a table that lists some technologies. I highlight especially 3 of them because they have high ability for scalability. So you have lithium ion, the hydrolysis of water, and redox flow batteries. Especially redox flow batteries, they show the lowest costs for storage. And so I'm going in more detail on this technology. So this technology was discovered in the beginning of last century, but suffered a great development by a professor, a lady in Australia, especially the vanadium-based redox flow batteries. So the difference between this technology compared to lithium is the redox pairs are dissolved, in this case in an acid solution, aqueous solution of sulfuric acid, so for vanadium, and this is pretty normal, though more recent research goes in the direction of non-aqueous solvents. But the present technology uses mostly vanadium and sulfuric acid aqueous solutions. And so here in the middle you have the electrochemical device, so the cathode, the electrodes and so on, and you have these pumps that make the electrolyte to circulate and charge and discharge depending on what you want. So I have here the equations for whom that wants to see equations. So the standard redox potential is for this technology is 1.25. Actually, the nominal voltage of this technology is 1.35 volts, since the concentration is that are used is higher than 1 molar. The energy density of this technology is in the range of 40 to 50 watt-hour per liter, which compared with lithium with a maximum of, present maximum of 250 watt-hour per liter, it's quite moderate. But price is nice. So for stationary applications, it may be a possibility. So the question now is, okay, I can store the energy in my house, it's cheap, it's expected that the cost per cycle of 1 kilowatt hour storage is 3 cents. So if you produce electricity, say by 10 cents per kilowatt hour plus 3 for storage, you can pay at your house the electricity for 13 cents plus taxes. This picture is mostly valid for Portugal. If you move north, the prices for photovoltaics increases. But for Portugal, this is really very attractive, unless the government puts some taxes on this. But it compares well with the price of electricity without taxes, that is in Portugal around 17 cents. The residential consumption, it's about 25% of the produced electricity. So if we address the residential and offices market with storage, we alleviate a lot the problem of dispatchability. We won't solve, we alleviate, especially for day and night. If we, for one season from another season, from 1 week to another week, this is another problem. We may discuss about that, but from day and night, I'll say, storing for 1 or 2 days, this is possible and feasible with this technology. Longer, we need other technologies, other solutions. But I want to share today with you a new advancement that combines harvesting and storage. So the idea is having a semiconductor. The semiconductor absorbs light and makes the charge separation, and then you can have an oxidation and reaction and reduction reactions going on. And instead of using this for producing electricity, you can use this for actually charge this redox flow battery. And this is, though some studies in the 80s, that was really addressed in this way just last year by our group and a group in Denmark. So this is kind of animation that shows charge, discharge. So you have here the panel, and with this panel you can harvest electrochemical energy. So you can harvest, transform in electrochemical energy, and also heat. So you can do a cogeneration of energy. And if you have a sample glass coated with a semiconductor, this promises to be quite cheap. So let me share with you just 2 results. So I heard about cadmium sulfide. We use actually cadmium sulfide coated with cadmium telluride to run this reaction. So this vanadium-based reaction is not the normal reaction. This is just with a standard redox potential of 0.6 volts. But we ran and we succeed to charge completely the battery this way. So you have here, you know, the band gaps of this semiconductor, cadmium selenide, together with cadmium sulfide. You have here the energy levels for the 2 reactions, and we succeed really to charge. But the problem of this semiconductor is unstable in the aqueous solution. So then we move to another system. Let me show this system. This system uses hematite. Hematite in alkaline medium is really very stable. We proved stabilities of thousands of hours, so it's no problem. So in this case, we use ferrocyanide, ferricyanide, and an anthraquinone for as redox pairs. Sorry, with a potential difference of 0.74 volts. And we succeed to actually to charge the battery this way. So now you can see here, we decide to move to other semiconductors. We have now bismuth vanadate, tantalum nitride, copper oxide. They are being studied for charging batteries. And so it will be soon possible to charge, you know, to to store the solar energy into an electrochemical fuel plus heat. Just for summing up, this approach allows a maximum conversion efficiency of around 10% if it is applied as a single semiconductor. And in my opinion, this should be the strategy because it's far cheaper and substantially cheaper than using photovoltaics. You combine heat and electrochemical energy, and there is another side effect that you can take advantage of. Since you charge the battery at higher temperature and you discharge at lower temperature, if the potential at these two temperatures is different, and especially higher at lower temperature, you have a thermoelectric effect that benefits the overall efficiency of the system. Okay, so I think I already reviewed all of these things. Just the acknowledgements. Thank you for your attention.
Thank you very much for this nice talk, and we have time for one or two questions, no more.
Very interesting presentation. Thank you very much. Do you have already enough experience to see the lifetime of the system you just presented and how many cycles you can perform with a decay of the performances?
Not of the overall system. We have tested hematite for water splitting for more than 1,000 hours without any decay, any observable decay. This was reported last year and was a record, actually. But it's absolutely stable. So let me say, I have no reasons to assume that for the photoelectrode you have any decay. Concerning the chemical species, anthraquinone is known as to be very, very stable. This was reported previously as a redox flow battery itself 2 years ago, 2015, by a colleague from MIT, Professor Azizis. And he observed no decay, but he tested for, I don't know, I can't remember, not for many hours. But you're right. There should be some degradation. The advantage of this technology compared with, say, the water splitting is the levels of energy in water splitting are the ones you know. And so it's very, very difficult to find, actually nobody found up to now, a single semiconductor that can do the water splitting. But using redox pairs, since there are many, many available, you can choose them, the flexibility is much higher. So this is the great advantage of using photoelectrochemical cells instead of using them for water splitting, to use them to store electricity or energy in electrochemical fuel that has a very high round-trip efficiency. That's another advantage.